So today we are going to present the video for the experiment 8, which is the heat transfer coefficient in dropwise and film condensation. So this is the name of student for our group, which is we have Lim Zehui, Muhammad Yusuf bin Omar, Saifullah Muamin, and Hafiz Nur Izzuddin bin Jimat. This is the table of contents for our experiment, which is we have introduction, objective, theory, working principle, experiment setup, methodology, results and discussion, safety procedure, conclusion, and references.
Okay, about the introduction, film-wise and dropwise are two forms of condensation when saturated vapor comes in contact with lower temperature surface. Condensation process will occur. In case of the film-wise condensation, the procedure moisten the surface and create a laminar vapor film can cover the entire area. The film can move downward and thicken as it picks up more vapor along the roots. Vapor condenses into smaller droplets and varying size on the surface when the condensation is modest.
So this is the objective for the experiment, which is to determine the heat transfer coefficient for dropwise and film condensation using the condensation process demonstrated here. So for the scope for the experiment, which is we will use two different type of condenser, which is dropwise and film condensation, and flow rate used in the experiment start from 0, 5, 10, 15, 20 liter per hour, and power that we'll use of our electrical heater is limited to 80 watt. Lastly, is type of fluid used is limited to water.
For the theory and working principle, condensation is the process where water vapor becomes liquid. It is the reverse actions of evaporations, where liquid water becomes a vapor. So condensation of vapor is needed in many of the processes, like steam condenser, refrigerator, and etc. So when vapor comes in contact with surface having temperature lower than saturation temperature, condensation occurs. So for this picture, showing that in film-wise condensations, the condensed liquid will wet the solid surface, and by forming a continuous film of condensate on the surface. So actually, in this picture, the this metal actually is the solid surface is actually wet by the condensed liquid. Next. So for this picture is for the dropwise. So for this picture is for the dropwise condensation. So you can see that the condensate liquid collects in the form of countless droplets of varying diameters on the condensing surface, and then these droplets fall down the surface very fast compared to the film-wise condensations. Next. So from the video, actually this one is the clockwise and this one is the clockwise. So you can see that actually the clockwise, the liquid drops very quickly. For the film-wise, the liquid actually wets the surface. Next. So for the dropwise condensations, as the bare solid surface is further available to condense. So the heat transfer coefficients and thus heat transfer rate are very high compared to film-wise condensations. But dropwise condensation also have its disadvantage, which is the heat transfer coefficient is difficult to predict, and dropwise condensation is difficult to achieve and generally occurs on oily or greasy surface. So dropwise condensation condition is very difficult to maintain and is unstable. So dropwise condensations, although its heat transfer coefficient is high, but is not commonly used in industrial. So for the film-wise condensation, due to the presence of continuous liquid film of condensate between the vapor and solid surface, so you can clearly know that the heat transfer coefficients and the heat transfer rate are very low compared to dropwise condensations. So the heat transfer coefficient value, but the advantage is, although it is very low for the heat transfer coefficient value, but for film-wise condensation, the heat transfer coefficient value can be predicted easily, and film-wise condensation is easily obtained and generally occurs on smooth, clean, and uncontaminated surface. For film-wise condensation conditions, it's very easy to maintain and stable, and it is more common use in industrial. So this is a figure. For the left-hand side is the film-wise condensation, and the right-hand side is the drop-wise condensation, which is drop-wise forms a droplet, and film-wise just wet the surface of the solid. Next. So this is the formula for us to calculate the heat transfer coefficient, and Q is the transfer thermal power, and we use MCP data to calculate the Q, and then CP is the specific heat capacity of water, and then A is condenser surface area, and then Ts minus Tw is the difference between the saturated vapor and the temperature difference between saturated vapor and the wall of condenser.
Okay, this is the experiment setup. So all of the component you can see here, there is tank, condenser, separator, water, jet pump, condenser of film condenser, condenser for dropwise condensation, cooler, electric heater, cooling water valve for film condensation, cooling water valve for dropwise condensation, pump valve, filling and drain valve, condensate valve, ventilation valve, safety valve, ventilation valve, measurement and control engineering, flow meter for film condensation, flow meter for dropwise condensation, temperature, film condensation inlet temperature, film condensation outlet temperature, film condensation surface temperature, dropwise condensation inlet temperature, dropwise condensation outlet temperature, dropwise condensation surface temperature, and tank temperature. So we proceed with the methodology. First, we need to power on the condenser. After that, open the water source. Then set the heater power and switch on. After that, we need to record the initial value into the table. Then we need to wait 10 minutes to stabilize the system. After that, we need to adjust the flow rate V1 and V2. Then record T1 until T7 in the table. Lastly, close the main water source, switch off heater and main switch.
Okay, for the result in the experiment, uh, we can see for the volumetric flow rate, the temperature T1 until T7 is below the 30 degrees Celsius. The average of the temperature we get is 24.5, and after the volumetric flow rate change to 5 until 20, T1 until T7 is increased until 101.3 degrees Celsius. So this formula we use to in this experiment, where T1 and T4 is inlet temperature, degrees Celsius, T2 and T5 is outlet temperature, T3 and T6 is surface temperature, T7 is steam temperature. So this formula used to the formula used to calculate the mass flow rate in the experiment, and Q to calculate the transfer thermal power, and lastly, next slide. Lastly, for the heat transfer coefficient, to using this formula, alpha equal to Q over area surface times with temperature, the difference of temperature. So the surface area is 0.00427 meter second, meter cube, meter square. Okay, for this result for the film condensation, so we can look at the table 1, volumetric flow rate for 0 liter per hour. For temperature 1 and temperature 2 is very closely each other, with 23.5 and 22.5. But for the volumetric flow rate 5 liter per hour is until 20 liter per hour is increased from 25.7 to 54.7. Next, for the table 2, is same. For the volumetric 0 liter per hour is stable for the average 24.2, but for the 5 liter per hour is increased from 95.6 to 101.3. Next. So this mass flow rate, heat transfer, thermal heat transfer and heat transfer coefficient for the film condensation. So for the 0 liter per hour is all value is getting a 0, and for the 5 liter per hour until 20 liter per hour is have the value, and the value for the heat transfer coefficient is increased while the volumetric flow rate increase. So this is a graph for the outlet temperature T2 against volumetric flow rate F1, and the second graph is graph coefficient heat transfer in film against volumetric flow rate F2. So this table for the DROPWISE condensation, so we can get the we can look at the 0 liter per hour. T4 until T5 is same value with the average 24.5. So for the volumetric flow rate 5 until 20 liter per hour is increased from 25.8 to 48.2. And for the second table, we can get the volumetric flow rate 0 liter per hour at T6 and T7 with 23.6 and 26.9. But for the 5 liter until 20 liter per hour is increased from 100 to 101.3. So this result for the dropwise condensation, and we can look at 0 liter per hour is the value is getting 0.2, and for the 5 until 20 liter per hour, the value of heat transfer coefficient is increased to. So this is a graph of outlet temperature T5 again volumetric flow rate, and the second graph is graph of coefficient heat transfer in film in dropwise condensation again volumetric flow rate F2. So this is a graph of coefficient of heat transfer alpha in film against volumetric flow rate F1 and F2. So for the F2 is a dropwise condensation. The value of the heat transfer coefficient is increased by the volumetric flow rate increase. But for the uh, film condensation is below the line of the dropwise condensation. So this is a discussion. For film condensation based on table, when we increase the volumetric flow rate from 0 liter per hour to 20 liter per hour, the outlet temperature, surface temperature, and steam temperature will drop while inlet temperature is mostly constant at 26.2 Celsius. Transfer thermal power Q is calculated by using this formula Q MC, and heat transfer coefficient calculate P times with T out minus T in by using this the formula alpha. For example, for the film conversion, when the volumetric Q times with when the volumetric flow rate Q over area surface times with T times with uh, the the difference of temperature, flow rate F1 is 5 liter per hour. The transfer thermal power is 243.02 joule per second. And for the heat transfer coefficient that calculate for film condensation is 9670 watt per minute. The graph of outlet temperature T5 again volumetric flow rate F1 is inverse proportion as the outlet temperature decrease when the volumetric flow rate increase. The graph of coefficient of heat transfer alpha in film condense again volumetric flow rate F2 increase proportionally as the heat transfer coefficient increase when volumetric flow rate increase. The graph of outlet temperature T5 again volumetric flow rate F1 inverse proportional as the outlet temperature decrease when volumetric flow rate increase. The graph of coefficient of heat transfer alpha in dropwise condense again volumetric flow rate F2 increase proportionally as the heat transfer coefficient increase when volumetric flow rate increase. Dropwise condensation has higher heat transfer coefficient due to the direct contact of steam with the surface, while from condensation the steam does not contact directly with the surface on the tube radar. It has to contact with the resistive layer of water film around the tube.
So for the safety procedure, this is the rules that we need to follow while conducting the experiment, which is first we need to wear our lab coat, which is provide protection of skin and personal clothing from incidental contact and small splashes. Other than that, was to prevent the spread of contamination outside of the lab and to provide a removal barrier in the event of incident involving a spill or splashes of hazardous substances. And then the second one, which is we need to wear our shoes or safety shoes. which is designed to protect against foot injury. Some of the most common causes, including a crushing, impact, and puncture. So the conclusion is the height, heat transfer coefficient, and the observed changes in the temperature parameter during the dropwise condensation when the volumetric flow rate is increased are consistent with the principle of heat transfer. Improved heat transfer efficiency from the higher flow rates results in a lower temperature at the outlet, on the surface, and in the steam, while the inlet temperature stay mostly constant. The high efficiency of heat transmission in dropwise condensation is quantified by the estimated heat transfer coefficient, which give a larger value to reflect this better performance. This experiment highlights how flow rate affect heat transfer efficiency and show how dropwise and film condensation are both beneficial in different situations. The findings offer insightful information for heat exchange system design and optimization, which will eventually improve energy efficiency and sustainability in engineering and industrial operations. So this is the references that we use for our experiment. That's all. Thank you.